You gotta get this color on. Okay, the lesson today has as its title, and this will be a lesson that covers today and tomorrow. Homework 2 tonight will be on this stuff, but we're moving into various methods for finding the real zeros of a polynomial. So some of those techniques you already have at your disposal, namely various factoring techniques. So you want to just add to your arsenal of tools for being able to factor and find zeros for higher degree polynomials. So in addition to factoring, we'll add to the mix division is one thing that will be the main focus of today. The remainder and the factor theorems that will go hand in hand with that. And the rational root theorem and Descartes' rule of signs. So those we'll do probably tomorrow. So let's start by just reminding ourselves how this even goes. I know we all did it last year. But this is, I think you'll, in the end, even though this might be uncomfortable for the first few seconds, as you get back into this, I think you'll be like, oh yeah, I do remember how to do this. So go ahead and set this up. Do the long division. Ready to go. See you in a minute. Oh my God.
But now I don't.
Oh, wait.
Wait, don't you never tic-tac-toe thing, right? Like, tic-tac-toe? Oh, I remember that. Like, hockey thingy. I forgot about remainder.
Go ahead, Come on up. He's coming back to you. Guys, help your table mates out. Remember the bonding part? Or what we're doing here? Here comes the.
Make it big.
That's big.
That's too big, man. Now what do I do?
Erase it.
Where's the eraser?
Do it again.
It's like Clara still saying.
Did you write too big or something?
I think so.
Do you think you can write smaller or?
Yeah.
Okay. So, am I right? This is something you all did in Algebra 2, right? Like last year?
Yeah.
This is good for you. If it feels good, do it again. Walk those same pathways in your brain. Refreshing your memory about how this goes. One thing that might be a little bit harder to come to, though, is how do we even interpret this result? Right? And that'll be the subject of the next slide I have up here. But you can already start thinking about that now, even. What are we doing when we actually do this division? Is it just like, just algorithmic? We just get an answer, but we don't know like what it means? For example, in this particular case, you got a remainder, didn't you? What was the remainder? If you got 3, then it's unlikely that you did it wrong, though it's possible. Okay? But if you got 3 as the remainder, good job. I'm sure you're doing great. But it still remains to be seen. Like, what do we even mean by a remainder of 3 in this context? I understand what it means, like, when I'm dividing cookies among friends and there's like leftovers. In some sense, is there like leftover here? And with polynomials, it seems more abstract maybe. So we do want to like figure out exactly what we've done. So we'll work on that. Neil's doing a great job. Did you want to voice an idea?
Well, I thought we could like answer it.
Yeah, sure. Go ahead.
Okay, so
What do
like,
you think?
for example, if you were dividing up cookies and it was like 7 cookies divided by, I don't know, like 2 friends, then
Yeah.
you'd each have 6, and then there would be like a remainder of 1 cookie.
You'd each have 3.
I mean, you'd each have 3, so it would be 6.
Yeah.
And then there would be a remainder of 1 cookie. And then since you were dividing it by 2, you would just divide the remainder by the dividend. Is that the word?
The divisor.
The divisor. So in this case, we would do 3 over 3x plus 2.
Yeah, so some of you already were asking me as I was walking around, like, what do I do with the remainder? How do I write that? So let me actually show you the answers to that on the next slide here. There are 2 good answers to that, one of which is what you just said. By the way, this is good. I like the fact that you're keeping track of negatives here. The other way I might do it here is to write this, right? Here instead, or somehow though, be careful. This one's not too bad, because notice that the coefficients on both the dividend and the divisor are all positive. That was nice of me for this first example, but they won't all be that way. So it'll be very easy. The thing I see most often, I feel like, is a sign error in your work, okay? So be very careful about how you manage signs. I always like to put minus and then whatever the product was each time, so that my work is methodical and all that. Another thing that you might do is you might move this x squared to be on top of the x squared here, like a placeholder, just like you did in elementary school. All right, so how do we report the result, especially when we have a remainder? 2 ways of reporting your result for division. So here's the first way. It's called polynomial form, and it only helps if I write these down here, these words down here. So dividend is the thing we started with, the big polynomial, the cubic in the last case, equals divisor times quotient plus remainder. That's why I named the functions up there the way I did. So that might be a little bit opaque. So let me just do it with cookies again. You have 22 cookies and you're dividing it among 7 people, say. We go back to elementary school on the right side of the board. So, well, what do we get? Well, everyone gets 3 cookies, and with what? Dividing by 7 times 3 plus 1. You see how that captures the division? In fact, in number theory courses, when we first say what division even means, this is usually given as the definition of division. This is what we mean. One thing we should note about this is that R of x will always have a degree less than d of x. Why? Imagine on the last problem that we were just doing, imagine that you got a remainder that was linear. What would that indicate? Given that the divisor was a linear thing, what does that indicate if your remainder is still linear? Say it again, Joe. You haven't finished, right? You could have done more division. So is that clear that this should always have, if this remainder were of a degree greater than or equal to d of x, then that means you could have done more division. Like, you're not done, right? So notice that this always has a degree 1 less than, at most, than the divisor, whatever the divisor was. So in the last case, the divisor was linear, so you saw that the remainder had to be a constant. Okay. So there's the result listed from the last one, right? You can also do it the way that some of you were suggesting, which is sometimes called fraction form. Dividend divided by divisor equals quotient plus remainder over divisor, right? So in the 22 cookies case, what do we say? We say, someone says 22 divided by 7 equals 3. Everybody gets 3 and 1 7, right? So that means everyone gets 3 whole cookies, and then we take the last cookie, divide it into 7 pieces, and everyone gets a piece, right? That's how that works. The same thing can be done here. In either case, notice, do you see, even if you don't want to do the work, do you see how you could go back and verify that you're right afterward? Yeah, just combine these rational expressions to get hopefully the one on the left. Or up top, multiply this out, add 3, and see that you get the thing on the left. But in all cases here, hopefully the equals sign means equals, right? They actually are equal, hopefully. So you're just re-expressing what you had originally in a new way. And one last bonus question. What happens in this problem if you let x take on the value 10? Question at the bottom says, if you do that, what elementary school problem have you just solved? So what I'd like to do is every x that appears up here, substitute a 10. What do we have up in the numerator? What's the dividend? 3,587. And then the denominator? So what division problem are we doing? 3,587 divided by 32. And the question is not the only thing up here. The answer is up here too. What's the answer? 112 and 30 seconds, right? Plug 10 in everywhere if you weren't with us just now and see that you're saying the same thing we just said.
Do you know what any number?
Yeah, I mean, I think it's worth mentioning that any time when we're working in algebra, that at any moment, that x could be like a number. Remember that that's what algebra does for us. It hopefully generalizes properties of numbers. In fact, our mathematical practice of the week is reason abstractly and quantitatively, right? That's one of the main things we want to have you do in math, is to think, like, come back to earth. Think big, and then also come back down. Like, make sure you're like, don't get lost. I like doing this because it reminds you not just that this is similar to what we did in elementary school. It tells you that this is exactly the same thing you did in elementary school, right? All right, let's try one more division problem. This time, I've made it a little harder, and also I'd like you to practice not just being very careful with a slightly harder problem, but also this new way of writing it. So maybe try writing it in one of those two forms, maybe as well. I'll come around and see how you're doing. More practice. It's been a while. If you got it, let me know. Not one you can do it in your head.
Is it supposed to be plus 2 or something like plus 7? Oh, wait, this is your J's. Wait, so would it be like 7 over 2? The remainder would be 2.
Remember, don't stop when it's linear. The divisor is linear. So make sure you keep dividing. Even if the numbers you start getting are not integers, just keep dividing. Remainder here will be a constant again. Has to be. Has to be.
X minus 4 divided by 2x plus 1.
I don't think you can do those. Yeah, but then you get, okay, times, you get a half.
Yeah, so
I don't know what to do. So wouldn't it be plus 7 halves? Do you get plus 7 halves?
That's like the original.
Which is 3.5.
You guys get 5 halves.
Negative 1 and 7 halves is an improper or mixed number. Yeah.
So you have to keep dividing after you get this. So if I get this, I will divide it like this.
Plus 7 halves.
Negative 1 half.
I don't even want to look at that.
Alright, the work for this is coming up.
No way, you didn't think it's possible. Do I get it?
I'm not sure yet what you want to do.
Tisha, I'm just so jealous. Oh, can I please have a Tisha? Yeah. Good.
What did it be?
Highlight of my day. The highlight of my day was yeah, I know. That means I can probably
Would it be negative 4?
Someone else you got a sticker. Would you be able to do the reporting on the, just to quicken the work here? She'll finish this up, and someone else can write. Who's got a sticker? Where are you? Someone, yeah.
yeah, Tisha has all the stickers.
Should I put down in both the forms too, or is this just fine?
Keisha's got it.
I'm so jealous.
Okay. All right, so negative 9 halves is the answer. Yeah, just write it over there. Negative 9 halves is the remainder, and if you got negative 9 halves as a remainder, again, it's very unlikely that you did it wrong. Okay. But notice that she doesn't stop here. She keeps dividing. 2x goes into 7x. Not a problem. 3.5 times. You know, we can do that. Or 7 halves times, she wrote. I like that. In polynomial form, it's coming up on the board. You gonna do fraction form for us too? Just for fun? Sure. I don't know.
He's just getting fancy.
Do you know how to do a fraction form? You can have it. That's one fraction.
So the remainder is 9 how?
All right. Let me direct our attention to another interesting question as she's putting that up here. What would happen if the thing we're dividing by, that is the divisor, is instead of some complicated polynomial, is just some polynomial of the form x minus a number, right? If that's the case, then the definition I gave you at the very start of this is written this way: d of x times q of x, divisor times quotient plus remainder. And this time I didn't make this r of x because I know the remainder is constant. Why do I know that? Why do I know the remainder will be just a number? I'm not writing r of x. because it won't involve an x.
Wouldn't it always be a number anyway?
It will not always be a number. You're right. The examples we've done makes that seem like you'll always get a remainder that's a number. Sometimes you'll get a remainder that's a function. Here I do know that it will be just independent of x, though. It'll just be a number, a constant. Why?
Because our divisor was linear, so the remainder has to have fewer x's.
Yeah, it has to have a lower degree than that. So we know that the remainder is at most constant. All right, so anyway, but if the divisor in blue is actually something very simple like x minus k, I want to ask you what would happen if you plug k into the original function. Given the fact that this is a way you can write the original function, what happens when you replace x in this equation by k? What does f of k come out to be here? What do you get? Yeah, don't you just get r? This will be 0. This will be something, but we don't care, because we're going to multiply it by 0. And you should just get the remainder. So what you've just done is demonstrate something called the remainder theorem. And if you want a proof of the remainder theorem, just look at the work we just did. That's it. That's a little proof. It's a kind of a thought experiment, but it's a very quick result to get. This is called the remainder theorem. It's a very powerful, even though it seems somewhat obvious, maybe, it's a very powerful theorem, if and only if. If you divide a polynomial by x minus k, then the remainder is r equals f of k. That's pretty nice. But it's also true the other way around. If r equals f of k, then that's the remainder that you would get. So you don't even have to do the division if you don't want. If all you care about is the remainder, you just plug in k. Boom. Yeah, right.
Wait, have you put these slides on the MCP?
I don't know if I put them up for this year or not. Good call. All right, so let's call the remainder theorem. You've got it. You've got your first theorem of the day.
So we're gonna have more today?
Have to wait and see. So exciting, I know. Barely continue. All right. Let's actually use this now as a result. Let's see if we can find. In a minute, I'm going to ask you. I'm going to give you a dividend of some kind, and you're going to and a bunch of divisors. I'd like you to compute just the remainder. Don't do the division. One could, but don't. If you did the division, you'd get the right answer too, but don't do that. Just see if you can get the remainder directly for each of these. You ready?
No.
So take this and don't do the division, but tell me, if you were to do the division, what would the remainder be here if you divided by this? If you're paying attention on the last slide, what does that mean? What's the theorem say? What's k here for this first one? Good, -3. The theorem said if you divide something by x minus k, well, in this case that would be -3, x minus -3. Then the result will be what? Just g of -3. So do you hear what I'm supposed to do on each of these? Don't do the division. Just calculate for each one of these the remainder if you were to do the division. And I'll call on whomever I like in 20 seconds from now. Okay? You ready? Just plug in the appropriate k value and tell me the remainder you get. Please. All right. Julie, do you have the first one yet? Huh? Do you have the first one yet? So you're plugging in -3 to the g of x, right? So just tell us what you get, right? When you do that. I'll come back to you. Claire, did you get b yet? -12. If you plug, what are you plugging into g? 2. You get -12? Try again. And yeah. And Ashaya, do you want to do C? Do you have it yet? All right, we'll come back to you in a second. So Julie, you plugged in -3. What's g of -3?
Oh, these are actually plugged in.
You get the second one? It's 0? Okay. Julie, did you get A yet? What'd you get? -3? Did you guys get -3 on the first one? Can I get confirmation on these? Is it -5? Are you sure? -5? You sure, Julie? Okay. And then see, who did I have doing that one? Akshaya. What'd you get there? -9? Alright, can someone just verify all these answers?
Yes.
Okay, good. Which one is most interesting to you?
The second one.
Why?
It's
What is,
divisible by,
yeah, why is B most interesting? Say it again, Pranav.
because it's
Listen,
divisible.
guys.
It's divisible by g of x.
Yeah, the reason, because I think the question still might be in your mind, like, this is neat and all. It's neat that I could find the remainder, but don't I normally want to do the division and like actually get the quotient as well? And the answer is like, well, maybe. But maybe we just care about whether it's a factor or not. Let's bring in the factor theorem, which is an immediate corollary of the remainder theorem, right? If the remainder is 0, that does tell you something interesting. If I split a bunch of cookies among a bunch of people evenly, and there are no leftovers, that's really an interesting thing to hear from you. What that tells me is that the number of cookies was divisible by the number of people there were. The number of people there are is a factor of the number of cookies. That would be especially important if we didn't have cookies and instead we had something that was indivisible, like cars, for example.
Why is that?
I was gonna say people.
We can't like split that. The United States. Can't divide that up. It's indivisible. All right. Again, the power of this very compact and somewhat simple sounding statement cannot be underestimated. Again, this is a biconditional. What this means, if you find out that x minus 7 is a factor of your polynomial, then it necessarily has to be the case that 7 is a 0. And the converse is true too, right? If 7 is a 0, then you know that it must be the case that x minus 7 is a factor. Okay? Biconditional. If x equals 7 is a 0 of the polynomial, that is, if you plug 7 into f and get 0, then it must be the case that x minus 7 is a factor. And the converse, if x minus 7 is a factor, then you know it must be true that f of 7 is 0, that is 7 is a 0. Right? All right, let's make this our last slide today. It's good. Let's practice this for some of you who have taken. I know certainly in AAF, if you were here for that, you did synthetic division. But if you had maybe the county version of Algebra 2, you may not have learned synthetic division. So I'd like you to do this both ways, and this is for people who know synthetic division already too. Because I think that for those who know synthetic division, you obey it, but don't understand it, right? So I think there's no tool we should use in mathematics if we don't understand it. So see, that's the reason I want you to do both. So that you can look at them side by side and see directly where the things come from and why you're allowed to do what we're allowed to do. For the sake of time, let me walk you through how this goes. You put your k value here, and then you're going to put your coefficients in order here. By the way, if there are any missing powers, quote unquote, and you need to put zeros for placeholders, that's true when you do long division too, right? And then, does this ring a bell? Drop the 3.
Yeah.
It's coming back. 2 times 3.
6.
Good job.
Figure 1.
Add. Multiply, add, multiply, add,
26.
multiply, right?
Oh my god, I'm so good.
And then add. You don't have to draw these arrows. I'm just trying to show you.
Oh yeah, I'm completely remember this.
6. So what does that tell you? It tells you that 6 is the remainder. The quotient is 3x plus 13 plus 6 over x minus 2. Okay? Do the long division so that this isn't voodoo. You'll see right away when you do the long division where all these numbers came from and why it even works. Try doing it side by side. The long division should only take you a minute to do it. And just keep in mind, even though this is very fast, very fun, keep in mind that this only works with linear factors still. So if anyone is asking you to divide by some crazy quadratic or something, you still need to know long division. And I think it's still helpful, maybe more when it comes to long division. It's a little more helpful in terms of you actually understanding what you're doing, maybe. I'm not sure how illuminating this is. All right, homework 2 tonight, please. We'll see you tomorrow for more discussion from this same lesson. All right, we changing your lives? I hope so.